Over the past 2 weeks, we've looked at the overall Crossrail project.
Three, two, one, go!
Understanding the construction process is essential to see why certain methods and technical decisions were made for Canary Wharf Station. Based on that, we'll now begin focusing on the station itself. In central London, most Crossrail stations were built to preserve the existing cityscape and made efficient use of underground space with minimal surface disruption. Canary Wharf Station follows this same approach but takes a unique path. It was constructed above water at the independent side of West India Dock to avoid interfering with the city structure and underground networks. While it shares the same goals as other stations, building over water required a very different construction process. Today, we'll explore that difference focusing on the cofferdam. Canary Wharf Station began not by reclaiming land but by building a cofferdam underwater. This allowed workers to block out water and carry out construction in a dry environment. Once the water was fully pumped out, excavation and structural work began. The team built 4 levels below ground and 2 above. After that, the temporarily drained space was later reflooded. Afterward, interior works such as escalators and ventilation systems were installed, moving the project toward completion. Unlike most cofferdams, the one at Canary Wharf was not dismantled after construction. Instead, it became a permanent part of the station structure, which remains in place to this day. Now, let's look at the full sequence of this underwater construction process. Starting with design adjustments, the process continues with ground investigation and selection of the construction method. Then, dewatering is carried out to stabilize the ground. Kick-on piles were driven in, followed by the connection of anchor piles and tie rods to support the sidewalls. Pre-stressing and full dock dewatering are then performed to secure the internal construction space. Once the cofferdam is complete, the main station structure is built inside it. Building on this, let's examine each step in more detail. Step 1. Design revision. The first step is design revision. Based on the initial plan, this stage involves adjusting or modifying the design to reflect actual site conditions, regulations, and stakeholder requirements. The original plan for Canary Wharf Station involved partially or fully infilling the North Dock to construct a station box over 300 meters long. However, this would have incurred excessive cost. Through design revisions, the station box length was reduced to 260 meters and construction was switched to a cofferdam method built in open water rather than land reclamation. This 40-meter reduction in station length had a significant impact. The longer the cofferdam, the higher the construction, equipment, and maintenance cost. A 40-meter reduction, about 50% of the total length, meant less steel was needed and excavation and dewatering were also reduced. In a high-cost construction environment like London, this translated to savings of several million pounds. The cofferdam method itself also helped cut costs. It enabled underwater construction without land reclamation, clearly defined the work area, provided a stable construction environment, and reduced the need for additional ground treatment. Through these design adjustments, the project achieved an estimated cost saving of around £26 million compared to the original plan. The next essential construction process for the cofferdam installation was ground investigation. According to the data collected from the ground investigation, the site's layer consisted of the following sequence from the surface downwards: dock sediment, made ground, river terrace deposit, Lambeth group clays, Opnor formation, Thanet sands, and chalk. The upper layers composed of sediments and clays did not provide sufficient support, so piles needed to be driven down to the more solid and compact lower aquifer layers, specifically the sands within the Lambeth group. These layers, characterized by high bearing capacity and drainage properties, served as a stable base for load distribution. Although the layers below become increasingly harder, drilling deeper was not necessarily the most cost-effective or efficient solution when considering construction costs and operational efficiency. After the ground investigation, the next step was selecting the appropriate construction method. Two methods were proposed during the cofferdam tender process. The first involved constructing a cofferdam with double steel plates and a new cut-off wall, allowing for construction in relatively open conditions. The second method involved driving Giken steel pipes down to the lambeth clay layer, then extending them into reinforced concrete walls. Both methods require piles to be driven to the lower aquifer for stability. However, the second method demanded temporary structures like props, increasing the construction difficulty and cost. Props are temporary support systems used to ensure safe excavation through complex urban environments. They were previously used in the construction of Paddington Station for Crossrail. Paddington Station, located in central London, required careful management of excavation stability and lateral pressure to prevent ground subsidence and protect existing structures. To achieve this, 50 props were installed, supporting up to 12,010 kN. In the actual construction of Canary Wharf Station, a combination of the two methods was used to suit the site conditions. The client had specific requirements, designed to avoid installing temporary support structures, props, inside the cofferdam, and minimize noise during pile construction. To meet these conditions, the first method's open construction environment was leveraged, while the Giken silent piler was used to install Giken tubular piles, which reduced noise. Concrete-filled piles were also employed. During this process, water pressure presented a challenge and a solution was needed to support the station's walls. Since prop installation was not allowed, anchor piles were installed behind the retaining wall to integrate with the cofferdam. Next is the crucial step of drainage and ground stabilization before beginning the construction. Before installing piles, 13 dewatering wells were used to drain the groundwater. High groundwater levels could cause water to seep into the excavated pit, risking flooding the workspace and collapsing the excavation surface. Lowering the groundwater level before the cofferdam installation is key to ensuring the safety and efficiency of the process. After securing ground stability, the next step was the Giken pile insertion. Two Giken silent pilers minimize noise and vibration while driving piles into the ground. The cofferdams on the east, north, and west sides were composed of 310 steel tubular piles with an outer diameter of 1290 mm, a length ranging from 18 to 38 m, and a thickness of 30 mm. These piles were hollow, and reinforced concrete filling was added inside to increase structural strength and support capacity. The steel tubular piles were installed using a combination of augering and hydraulic insertion methods. Augering involves using a rotating spiral blade to excavate the ground for pile insertion, while hydraulic insertion pushes the pile into the ground using hydraulic pressure, utilizing the reaction force from surrounding piles to minimize noise. During the initial installation, both augering and hydraulic insertion were used, and when reaching the Lambeth group clay layer, the final 0.5 m was driven without augering, ensuring water tightness. In the design for connecting the two steel tubular piles, a PP clutch was chosen instead of previously used PT clutch. Unlike the PT clutch, which has a single large grouting space, the PP clutch is divided into three smaller grouting compartments. The outer two compartments were filled using grout sacks made from fiberglass or synthetic mesh materials, while the middle compartments was directly grouted without sacks. Next, the ankle piles and tie rods were connected to support the cofferdam walls, preventing them from bending or collapsing. The primary structural support for the cofferdam walls was provided by 160 temporary anchor piles installed inside the dock connected to the Giken pile wall by tie rods. Next, pre-stressing was carried out. To prevent inward movement when the water was removed, hydraulic jacks were used to apply a force of around 100 kN per meter to the pre-tensioned walls. As a result, initially, the wall was displaced in the opposite direction of the excavation. However, once the dock was drained, the wall moved in the direction of the excavation. Managing this tilt was critical, as the excavation site was surrounded by major buildings over 45 stories high, with more than 15 structures within a 400 meter by 400 meter area. Therefore, it was essential to monitor any subsidence during the construction of the waterproof barrier. 21 inclinometers were installed on the geeken piles and 16 on the anchor piles, continuously monitoring any tilt. If tilting occurred, reinforcement works such as adjusting anchor tension were carried out. Although it seemed nearly finished, one wall remained to be constructed. On the opposite side of the space where this wall was to be installed, there were the foundations of existing buildings and structures, which made it impossible to install anchor piles. Therefore, after draining the dock, a cantilever support wall without braces was installed. This wall relies solely on the rigidity of the piles and the passive earth pressure from the soil layer installed in front of it, without the need for anchors or internal supports. One might wonder why this process had to happen after drainage. The reason is that the secondary second pile work needed to ensure water tightness, which would be difficult to achieve with the imprecise concrete placement underwater. Therefore, the work was carried out after the water was drained. Another question could be why install a new pile wall when there was already a foundation of an existing building on the south side? The answer is that the existing structure was not designed to resist dock water pressure but was merely part of the structure built during the dock's waterfront development. To facilitate the 26-meter deep excavation, a stronger and more resilient wall was needed. Hence, the decision to install an additional second piled wall. Thus, the installation of the cofferdam was completed, paving the way for the main station structure construction. This week, we cover the planning of Canary Wharf Station built over water, the cofferdam construction process, and how it differs from typical subway construction. Next week, in week 8, we'll discuss the building process, including the top-down construction method. In week 9, we'll focus on the roof garden, roof structure, and the materials used. In weeks 10 and 11, we'll wrap up the presentation by discussing the overall story of Canary Wharf and the selected building.